All right. So Thursday we talked about robots in manufacturing automation, right? So why is it that we use a robot? Or why is it that we use an automation system? Anybody remember? Yeah.
For jobs that are dirty, dull,
Dirty, dull, dangerous jobs. So we like to use automations or robots for dirty, dull, dangerous jobs. Um, what do we need to consider when we're going to what do we need to consider when we're going to specify a robot or specify the components of an automation system? Just very quickly. We made a whole list of these things on Thursday. So when we're doing dirty, dull, dangerous jobs, what's one of the things we consider? So the work envelope. So we need to consider the work envelope, yep. The cost, the GOST. And so that's both the cost of acquiring the system, but it's also the cost benefit of using the system, right? Because it could make the cost of production go down. So work envelope cost, what else do we need to consider? Yep. Say again?
Can you maintain staff?
Can you, yeah, do you have staff to maintain it? Do you, as soon as you install your first robot, is everybody else going to quit because they're afraid they're going to get replaced by a robot? Those are things to consider. So staffing. Anything else that's important here? So when it's dirty, dull, and dangerous, dirty, dull, dangerous jobs we like to have robots for. We need to consider the work envelope, the cost, the staffing needs of the company. What else? Any major considerations here besides those things? I mean, there's things like the, what do we say, the environmental conditions where it has to operate. Is it going to be underwater? Is it going to be inside a furnace? Things like that. Cost, staffing. What about the mass that needs to move? So how heavy are the things that need to move? You had something?
I was going to say the rate, cycle time, speed.
Yeah, that was the next thing I was going to say is how fast you need to do it. And if the job is dangerous enough or dirty and dull enough, we might even be willing to add cost to add the robot. Now, the other thing people automatically jump to when we're adding a robot is we feel like it's going to be more repeatable and it's going to be more reliable. Does that seem intuitive to everybody? We feel like a robot should be more repeatable or more reliable than a human. And I think that's especially true when we're replacing the dull jobs. Because a robot's going to at least do the same thing that it does every time until it wears out. Whereas people over time are going to sort of change the way that they interact with the system. So in the morning, there's not especially a robot. It was I guess it is. It wasn't really a robot, but we were using we were building a sensor, an automated sensing system. And the purpose of the sensing system was to judge whether or not golf club shafts were manufactured correctly. So what gets the golf club shaft or the golf club from the rack in the store to the cash register? If you're going to sell golf clubs, what makes somebody decide to buy one? Yeah, they pick it up, they look at it, they do a couple swings, right? Maybe they look at it some more, then they walk over and they pay $600 for it. That's pretty much how we decide to buy golf clubs, I think. maybe it's $6 instead of 600. It depends on who we are. But so this golf club shaft manufacturer, so they made the shafts. They found that the failure rates for the shafts would skyrocket the day after the Red Sox lost. So if the Red Sox had a good game, no problem, failure rate's normal. The Red Sox lost, failure rate skyrockets. That's because the guy at the end of the line that does this is throwing them away because he doesn't like any of them because he's mad. So sometimes robots can be more repeatable, especially in those dull jobs where we want to get rid of those people. But I think this pretty much covers it. We have to understand these things in order to specify what robot we're going to use and decide how to use it inside our system. Is there anything important that's missing there? Anybody? I mean, you may say the software that you're going to use and things like that, but that sort of comes down to staffing. Do you have people that can understand that, or can you acquire people that can understand that? I would say, I know some engineering professors, they would say, we don't care about the cost. We're engineers. We want to develop the new technology. We want to do these things. We don't care about the cost. Anybody heard that? Anybody ever heard one of their professors say that? Doesn't matter how much it costs, figure out the right way to do it. Anybody? You have? Yeah. I think we do still need to consider the cost. But the cost doesn't really matter. And I think you could even put staffing into cost. The cost doesn't matter if we can't understand this part, right? So if we can't physically solve the problem, so if we can't move the parts that we need to move to the right position in speed, so what are the units? You guys know engineering math? Just a bunch of word problems. Cancel the units. So what are the units that we have here? Yep. Well, so we've got area, so we've got length. 3 times length to the third. We have length there. We have units for mass, so pounds, kilograms, something like that. And we have units for velocity, right? And so that's length. This is cool, because we're engineers, right? Now that we have units, we can do math. What I want to do today is concentrate mostly on this work envelope question and figure out how do we know what our work envelope is? How do we know we're going to accomplish that? So let's look at work envelope. So how do we define the work envelope of a robot? We said we can use length to do it. But what makes the work envelope be what it is? Yeah. So how far it can reach. Right, and so if I was a robot and I'm mounted to the floor here, I can reach, I get 2 arms, that's cool. Robot mounted to the floor, I get 2 arms, so I can reach out like this. I can reach up over my head here. We might call this a spherical work envelope. Sort of mimics a sphere. Now I can change the sphere a little bit and get a little bit more work. If I was doing more yoga, I could do this more, right? Things like that. So how far it can reach can define the work envelope. what goes into how far it can reach? So how many, how am I moving here? I got a joint here at the waist/legs that I'm moving. Oh, I can move it this way too. It is sort of like yoga. Is it here? Okay. So how do we describe that? Because it's not just how far I can reach, it's how far I can reach as I move. So what do we describe that? Is it not just reach? Yep. Degrees of freedom. How far it can reach. Within the different degrees of freedom, right? We break this one free, now I can reach like, I'm done dancing. So we want to talk about the degrees of freedom for our robot, as well as, and so what does it mean when we have a degree of freedom? What do we mean when we talk about degrees of freedom? How do we create degrees of freedom? Or how do we restrict them? We do this in dynamics, right? Everybody's had statics and dynamics, right? I could teach those two classes in 30 seconds. Ready? Statics, dynamics. Okay, it's more than that though, right? Because we're controlling the motion too. So how do we create degrees of freedom? Or how do we limit them? Yeah. By the types of joints we use, that's one great way to do it. And what the joint does is it limits the motion in one direction or another direction, right? Right. And so the degrees of freedom and the length of the members of the robot arm, or whatever you want to call it, the length of the members and the degrees of freedom will define what the work envelope is. And so a simple example here of something sliding along a rail. So how many degrees of freedom do we have here? Just sliding along the rail. 1, without it to rotate this way. 2, right? If we have a plane, so who's played air hockey? Right, how many degrees of freedom? 2? Is it 2? Yeah. Can rotate and it can move. So we can put different things in our joint mechanism. We have 3 with our air hockey because we got the X, Y, and the rotation. And so here, when we've got our 4-bar linkage, how many degrees of freedom? And with our industrial robot, how many we got here? 1, 2, 3, 4, 5, 6. And so again, it's this combination of the length of the members and the degrees of freedom that will specify where the work envelope goes. And again, what's the purpose of all robots? What do they all do? What do all robots do? Position and manipulate an end effector, right? So we have the position and orientation of our end effector. There's math that lets us figure it out. We won't do that math as part of this class, but know that there is math and that there are computers that solve those math problems. But we got our... All right, and so we've got different ways to get different amounts of degrees of freedom. So here our block is sliding like this. So it's limited like that. It can't rotate this way. It can only slide this way. here it's going along this way, and it's rotating at the same time. So this is like one of those office chairs where the only way to make it go up and down is to spin it around. And this is like one of those office chairs that will go up and down and spin around independent of each other on the top. Yeah, there's different ways that you can put mechanical devices together to achieve different degrees of freedom, these things. There's also, when we look at industrial robots, we really talk about two major types of robot. You've got parallel, parallel kinematic manipulators or machines, and you've got serial robots. And you guys have seen all these in motion? Oh, come on. These are boring. There we go. All right. And so, what kind of operation are we doing here? Pick and place. So this is a traditional pick and place operation. Robots are really good at pick and place operations. What do you notice about this as it's going? So as we go through, yep. So it knows the difference between the three objects, and it sorts the three objects differently. All right, so we can identify different objects. So it's got a vision system, some sort of system that can identify the objects, and it can sort them differently. The other thing is it's got a very limited range of motion there, right? It was moving maybe 6-8 inches back and forth. And so when we build a system like that, it actually takes a fairly large footprint to get that small of an amount of motion. But what it can do is that it can move very quickly. It's very rigid, and so it can repeat that motion very quickly. And so you get that. So in a serial robot, we would have the gripper out here, right? And we'd be moving like this, grip it, put it down. We have to go through several motions to get to that spot. And we're moving all of the mass of all of this arm as well as the mass of the object through all of that. So you can't accelerate as fast with that larger serial robot in order to make those motions. Okay. And so these are very flexible because you can have different kinds of joints in them. You can control the degrees of freedom however you want as you build a serial robot here, because you're not limited to have all the same kinds of joints for all of the objectives. This is a gantry robot, or a 5-axis traveling bridge CNC mill. Now remember, we talked about on Thursday that some people will consider a CNC machine to be a robot, some people won't consider it to be a robot, and it really depends on your definition as you're doing it, whether you're going to call it a robot. I think it has all of the components though required. And of these serial robots, there's really 5 basic configurations. We got our Cartesian or a rectangular robot like this one. And here is a cylindrical robot, so it can spin around, and it's got a joint that comes in and out, and articulation at the last end effector. As we look at these work envelopes here, you'll see almost all of them have an area that they can't reach. So almost all of these robots will not be able to turn completely around. They're typically limited there. Work envelope. Another very common robot that we're going to see in industry is a Scara Robot, where we've got a bunch of rotational joints connected together. And here you can get almost the entire 360 degree of rotation, but it's got to come from one side around to the other side to complete it. All right. So we got different types of robots, different methods for building the robots. So as we look at these different robots, then we've got our different types of ways to build them. As we specify, we need to make sure that it can fit within our work envelope. It has the capacity to pick up the mass. And then again, if we're looking at purchasing a robot, can we afford to do it? Is it going to be able to do the job and save us enough money? And all of those things. So that's all going to go into our specification of what robot and our automation system. I'm going to end the class a little bit early today. We will have class on Thursday this week. No class Monday next week because it's a holiday. And we will have class on Thursday next week. Next week in lab, you're going to be working on the industrial robot that's in the lab as your lab exercise, going through some exercises there. On Thursday this week, we're going to go through things that you need to know before you arrive at the lab. Next week, you're working on the automation exercise inside a spree now, correct? And they posted the assignment to hand in for that. Okay. And again, that's due at the end of the term, but don't wait until the end of the term to finish it. If you get it finished sooner, then that'll be good. And so next week you work on the robot. The week after next, we're going to work on PLCs, programmable logic controllers, and we'll spend the rest of the class doing that work. Okay. Thanks.